Okay, so we're going to start with NMR today, and I'm going to stop close to 9 because then I need to talk about today's experiment so that we can get it done, preferably before noon. So last time we went and we talked about the x-axis, the chemical shift axis of the NMR, and said that one of the things that we'll find in the x-axis is that it will tell us about the type of hydrogen or the electronic environment around the hydrogen, and so we'll eventually be able to use this type of a chart to tell whether the hydrogen is attached to a benzene ring or an oxygen or a halogen or a double bond. But before we get to that point, we talked about how many hydrogens one would expect to have, or how many peaks you'd expect to have for a particular molecule. So the idea of chemically equivalent sets of hydrogens, and that's what the homework was on. Today we're going to kind of continue that and talk about some of the other pieces of information that you get from an NMR spectrum. Ideally, we want to work up to the point where if I give you an NMR spectrum, you can figure out the structure. But we'll start with trying to match up the peaks to the structure, to a given structure. So first thing that we get out of an NMR from the chemical shift, the position of the peak, is the electronic environment around that hydrogen, which will tell us what type of hydrogen it is. Alkane attached to a carbon with an oxygen, or a halogen, or a double bond. The second piece of information that we use is the height of the peak, or more accurately, the area underneath the peak. It turns out that the area underneath the peak is proportional to the number of hydrogens that make up that peak. It's kind of like GC. So the area under the peak is going to represent the ratio of hydrogens. And if we look at all the peaks, then we'll be able to determine the ratios of the hydrogens and figure out how many hydrogens are under each peak. So here's the spectrum, the NMR spectrum of methanol. So what we have is we have 3 hydrogens of the CH3 group that are all equivalent because of the rotation. And then we have the OH, which is different. So I would call each one of these methyl hydrogens A, and then I'll call the other one B. Now, you could make the assignment on this spectrum because you could look at this and say, well, which peak is the CH3s and which peak is the OH? Well, the bigger peak is going to be the CH3s because there's 3 hydrogens, and the smaller peak is going to be the OH because it's just 1 hydrogen. This, looking at the areas, is called the integration of the peak. And in the older instruments, the integration had to be done electronically and basically by doing certain things that I'm not going to get into. Nowadays we can do it digitally. But even when we do it on a new system, it still has the old way of marking the integrals. So the integrals are actually these S-shaped curves. And what we had to do in the old days is we had to take, and basically the integral mark starts here, and when it reaches a peak, it adds up the area underneath the peak, and then when you go back to a baseline, it goes back to being flat. So the integral is actually the distance between these 2 plateaus. If you measured the distance here between the beginning plateau before the peak and the peak plateau afterwards, that height is proportional to the peak area. And for this smaller peak, we would go from here to here. So that would be proportional to its peak area. Nowadays, with the computer, we actually would stop the S's and we would put individual S-shaped integral curves over each peak. But that's more detailed than most of you need to know. Okay. So what we had to do, if we were doing this by hand, is take a ruler out and measure the heights of those peaks in millimeters or centimeters, and then we would divide them through to figure out what the ratio of the hydrogens were. Now, when you see a spectrum like this, and you'll see different spectra during the course of the rest of the semester, these ones are actually simulated from a Macintosh program, and basically I can put these grid lines on here. So if I wanted to get the height of this, I would just count the number of like grids or blocks. So for this peak, I would have 1, 2, 3, 4, 5, 6, 7 and a half, roughly, blocks is the height of that peak. And then over here, I've got 1, 2 and a half blocks. So you do that for each peak. Now, on the newer instruments, it actually just prints a number below the peak, and then you can figure out what that. You don't even have to measure these with a ruler. But you still have to determine the relative ratios. So just like in an empirical formula calculation from a long time ago, like maybe the second month of general chemistry, what you have to do is, once you have all the integral areas, you divide through by the smallest number. And so in this case, we would divide each integral by 2.5. So if we divide each one of these by 2.5, we get 3 for the big peak, and we get 1 for the smaller peak. Okay, that means that the area is 3 to 1 in its ratio. Now, that doesn't mean necessarily that there's 3 hydrogens to 1 hydrogen. It just means that the ratio is 3 to 1. If this molecule had a grand total of 8 hydrogens, then it would mean that there's 6 hydrogens here and 2 hydrogens there. So you almost have to know the molecular formula in order to make sure that your integration ratios add up to the correct number of hydrogens. And if you saw a ratio of 1.5 to 1, that would mean that you'd have to multiply each one by 2, so that a 1.5 to 1 ratio would be like 3 hydrogens to 2 hydrogens, just like an empirical formula. Okay? So you'll have to do this for some spectra. Other spectra that I use just have like 3H and 2H over the peaks to tell you that they've already been integrated. But anything that comes from our instrument, you'll have to divide through the integrations to figure out the ratios. So that turns out to be a pretty important piece of information. Because if I count up the number of hydrogens and there's 3 hydrogens under a peak, well, chances are that's going to be a methyl group. Or if there's 2 hydrogens under a peak, it's a CH2. Or if there's just a single hydrogen, it's definitely a CH. So from the peak position and then from the integration, I can get a lot of information about the pieces that I'm going to put together. Okay, and again, the peak position, in this case, the hydrogen attached to the carbon is attached to an oxygen. So it's showing up between 3 and 4 parts per million. The OH we're not going to really do much with because it could show up anywhere. But in this case, it's showing up about 3. Okay? So the chemical shift of at least the CH3 tells me it's attached to a carbon attached to an electron withdrawing. So that's how we're going to try and piece the information together. Okay? So we've got integration, we've got chemical shift. The third part that's probably the most important and most useful is what is called spin-spin coupling, or it's also called splitting. Okay, here's the spectrum of ethanol. This is CH3, CH2, OH. Okay, it's the same here, but it has to be drawn a little bit differently. So we'd expect in the CH3, CH2, OH spectrum to see how many sets of non-equivalent hydrogens. 3. The CH3 would be, I'll call these A, I'll call CH2B, and I'll call the OHC. So I expect to see 3 chemically equivalent sets of hydrogens. But notice that I see more than 3 peaks in my spectrum. I see 4, 5, 8 peaks. Okay, definitely more than 3. Well, these come about because of splitting, because of the coupling of the different nuclei. And the way to explain this is, I'm going to go to this one. We've seen the effect of shielding and deshielding. In other words, the nucleus has electrons that surround it. Those electrons are going to orient themselves opposed to the magnetic field. So the number of electrons around the nucleus affects its position on the chemical shift scale. Well, that's not the only thing. The electrons that surround it aren't the only things that add or subtract a magnetic field to what the nuclei feel. It also turns out that the neighboring hydrogens also influence the chemical shift of those peaks. So for instance, let's look at the CH3. Okay, the CH3 hydrogens have as neighbors the CH2 group. And by neighbors, I mean the hydrogens that are attached to the carbon that are next door. Okay, not 2 bonds away, just a single bond away. And so the CH3 then has 2 neighbors, the CH2 group. Well, it turns out that those hydrogens, if they're acting like little bar magnets, can either be aligned with the field or they could be aligned against the field. And whether they're aligned with or against is going to add or subtract to the field that the nucleus feels. Just like when the electrons were oriented opposite the field, they influenced the amount of magnetic field you had to apply to get the resonance phenomenon. So it turns out that for these 2 hydrogens, the 2 neighboring hydrogens, there's 3 possibilities for orientations. They could both be aligned with the field. They both could be aligned against the field. Now, if you go back and you remember about shielding and deshielding, when the electrons were oriented against the magnetic field, then that led to shielding, right? If they were aligned against the field. So in this case, that means that when both of these nuclei, both of these little tiny nuclei are aligned against the field, I end up shielding my peak. Right? Just like the electrons were shielding. And we hopefully, if not now, we'll remember in a couple weeks that the direction of shielding was to the left. Right? The TMS is shielded. So peaks that occur to the left, or I'm sorry, the peaks that occur to the right, the way you're looking at it, are shielded. Peaks that occur to the left, in this case, the hydrogens aren't opposing the magnetic field, so therefore they are deshielding. So if both nuclei are with, or both nuclei are against, we're going to end up shifting the magnetic fields. Did you guys get this last week? That's the one from last week. Okay. So we've got shielding and deshielding. So that's going to shift the peak either to the left or the right, depending on the orientation of those 2 hydrogens. Now the middle, which is really the true chemical shift of the CH3s, in this case you're going to have one oriented with the field, one oriented against the field, and they're going to cancel each other out. And there's 2 possible orientations for that. You can have the HA up and the HB down, or you can have the HA down and the HB up. So there's 2 different possibilities of having one with and one against. What this leads to is the splitting of the original peak. Without the influence of these two guys, these two hydrogens, the methyl would just be a single peak. But because of the three possibilities, that peak then gets split into three. So we see what's called a triplet. We'll see one peak, then a middle peak, then a third peak. And when we have three of those in that pattern, that's what we call a triplet. So we see a triplet peak. The single peak, the single methyl, has now been split into three peaks. And the intensity of those three peaks is given by the number of possible orientations. So on the wings, you've got just one orientation of both up, both down. But in the middle peak, you've got two orientations. And so that means that the relative intensities of this triplet are 1, and then the middle peak is going to be twice as high, and the third peak is going to be, again, a relative area of 1. So we end up forming what's called a 1 to 2 to 1 triplet. And where's the 1 to 2 to 1 triplet in the spectrum of ethanol? Well, it's where the CH3 would be. And CH3s, by and large, are going to occur between 1 and 2 parts per million. So in terms of our triplet, there it is. That triplet is the CH3 group. So the splitting occurs because there are neighboring hydrogens. And the neighboring hydrogens, because they act as little bar magnets, they can be oriented with or against, and all those possibilities then influence the methyl group, and instead of getting a single peak, we get it split into 3 peaks. Okay, does that kind of make sense? Well, now we're going to look at the CH2. And for the CH2 then of ethanol, the CH2 here, I'm only going to consider the neighbors of the CH3. Okay, what we're going to find is that we only look at the neighboring hydrogens that are attached to a carbon atom. So the OH is not going to be considered a neighbor. Only the hydrogen attached to the carbon. So if we look at this, how many neighbors does the CH2 have? It's got 3 from the methyl group. So I can do the same kind of analysis. I can say, okay, all 3 of those hydrogens could be oriented with the field, or all 3 of those hydrogens could be oriented against the field. And again, we would have shielding and de-shielding. On the left, we would have an orientation that is de-shielding it. On the right-hand side, we would have an orientation that is shielding it. That's shielding those CH2 nuclei. But now, because I have 3 nuclei, I would have the possibility then of having 2 oriented with the field and then 1 oriented against the field. Okay, I'm never going to have a situation where they perfectly cancel because I've got 3 things. So I could have 2 oriented with the field, 1 against, or I could have 2 oriented against the field with 1 oriented with the field. And then you can have 3 possibilities for each one of those situations. Because there's 3 ways to orient 3 things, 2 with, 2 and 1 against. And so what happens? My CH2, under the influence of the 3 neighbors, gets split into now 4 peaks. And those 4 peaks are called a quartet. So in this case, I would end up with a quartet of peaks. And looking at the relative ratios of those, the relative ratios would be 1 to 3 to 3 to 1. Because there's 3 orientations for each of the 2 with, 2 against, or 2 with, 1 against. Where's the quartet? That's what this is called, is a quartet. The quartet in this case is right here. It's the quartet of peaks next to the single peak. That's the CH2. Why is its chemical shift so much farther to the left, bless you, than the CH3 was? Well, because the CH2 is attached to an oxygen. So that causes it to be deshielded. So splitting happens because of neighboring hydrogens. Now, there's a general rule for this, bless you. All right, everybody okay up to this point? So we saw a CH2 group split protons into a triplet, a CH3 group split the protons into a quartet. So what's the rule then that we can use to predict the patterns and how many peaks we would see? Well, the rule is n+1. In other words, the splitting pattern of a nucleus is given by n+1, where n is the number of neighbors. Okay, the n corresponds to the number of adjacent or neighbor protons. So in other words, the hydrogens that are attached to the carbon that are next door. And the caveat is that we only count neighbors that are attached to carbon atoms. Okay, those are the only neighboring hydrogens we're going to have. So that means that if you have no neighbors, then you're going to be a single peak because there's no influence. If you have one neighbor, you're going to see a doublet peak. If you have two neighbors, you'll see the triplet as we saw, and if you have three neighbors, you'll have a quartet. Now, the 4, 5, and 6 are not for proton nuclei, they're for other nuclei that we look at. So we're just going to deal with, as pure coupling patterns, singlets, which is no coupling, then doublets, triplets, and quartets. We will see patterns that have 5, 6, or 7 peaks, but I'll explain where they come from in a minute. Okay, so that's what we get. The key thing to remember is it's n+1, where n is the number of neighbors. That means that if you see a triplet peak, the triplet peak means that it has 2 neighbors. If you see a quartet peak, it means that it has 3 neighbors. Okay. I'm not going to tell you how you could screw that up. In other words, what you could get confused about. If you look at a triplet, you might think, I'm not going to tell you. You could figure that out on your own. But it's not that, it's the neighbors. In other words, it's not how many protons you have, it's the number of neighbors that gives you the splitting patterns. So if you got 3 neighbors, you're a quartet. If you got 2 neighbors, you're a triplet. The integration tells you how many hydrogens you have. Right? The area underneath the peak will tell you whether it's a CH2 or a CH3. But then its splitting pattern will tell you what's next to you. So if you have an integration of 2 hydrogens, you're a CH2. If you're a triplet, that means you got another CH2 next to you. And so that kind of information now lets us put together the structure by using integration, chemical shift, and now splitting patterns. Okay, so n+1 is what we're going to be working with. All right, everybody still kind of with me? There are some rules for coupling or for splitting, and that is that equivalent protons don't split each other. So if you've got a CH3 group, those 3 hydrogens, since they're equivalent, they don't split. If you have protons that are bonded to the same carbon, they will usually not split each other because they're equivalent. On the other hand, if they're not equivalent, they will actually split each other. And we'll get to examples of that later on. Protons on adjacent carbons normally split each other, normally couple. And once you get 4 or more bonds away, you won't see coupling. Actually, for most of what we're going to do, once you're not the neighbor, you're next door, you're like the next door, that's not going to couple either. So we're only looking at direct neighbors that are doing the coupling. Now, there's one big exception to predicting the rules, and that is an isopropyl group. Okay, so in an isopropyl group, and this is an example, but I'm going to rewrite it. In an isopropyl group, you've got 2 CH3s and the CH. Now, if I would ask you, okay, how many sets of hydrogens are equivalent in an isopropyl group, are the 2 methyl groups equivalent to each other? Yes. So whenever you have 2 methyl groups attached to the same carbon, they're 9.5 times out of 10 going to be equivalent. So the CH3s would be equivalent to each other, and then the CH would be different. Now, the rule is that if you are equivalent, then there's only one set of peaks. So what would the pattern be for the CH3s? How many peaks would I see for those 2 CH3 groups? How many neighbors do the CH3 groups have? Just one. Okay? The CH3 is attached to CH2. This is its neighbor. Okay? We don't go more than 1 bond away. So each of the CH3s has a single neighboring hydrogen. That means the CH3 is going to show up as a doublet. And over here on the spectrum, if you expand this peak, you can see that this is the doublet. So this turns out to be the 2 CH3 groups. Now it's big because it has an integration of 6 hydrogens, but it's a doublet. Now normally, for the CH, if the CH is attached to equivalent groups, then it only sees one set of equivalent groups. Okay, in other words, under most circumstances, except the isopropyl, if the CH was attached to 2 methyl groups that were equivalent, it would be like the CH is seeing just one methyl group, and so it would be split into 4 peaks. But in this case, in the isopropyl case, the 2 methyl groups, despite the fact that they're equivalent to each other, they're not equivalent to each other from the viewpoint of the CH. So the CH actually sees 6 neighbors. Okay. So this CH is going to see actually six neighbor hydrogens in an isopropyl group. Now, the n+1 rule can be used as an estimate of number of peaks once you get above 3 neighbors. So in this case, those 6 total neighbors, the 3 from here and 3 from here, that's going to give me roughly 7 peaks in my spectrum. And I'll explain exactly where those 7 peaks come from in a minute or two. Okay, so what you can see is that in this case, this peak labeled C is the CH, and it has a grand total of 1, 2, 3, 4, 5, 6, 7 peaks. And so for an isopropyl group, you're always going to see a 7-peak pattern and a doublet. That's a telltale sign that you have an isopropyl group in your molecule. Otherwise, if you're a hydrogen and you have 2 equivalent groups on either side of you, you just see a single group. Okay? But unfortunately, this is the exception to the rule. Okay, so one other thing, and then I'll show you a couple of examples, and then next week we'll work on some spectra and try and match them up. the distance between the peaks in a multiplet is what's called the coupling constant. So if you had a doublet, peak, the distance between those two peaks is what's called J, the coupling constant. And the coupling constant is measured in hertz. So what we would actually do on the computer is we can tell the computer, tell us the distance between those two peaks, and it'll say it's 5 hertz or 7 hertz or 10 hertz. In the triplet, there's two distances, and they should be the same. You would have then the distance between these two peaks is going to be equal to each other, and that's also then the coupling constant. So the distance between the peaks in a multiplet is the coupling constant. Now, what's going to become important later on is that the coupling constant is not dependent on the strength of the external field. To restate that, the coupling constant is constant. It will not change when I go to higher and higher magnetic fields or bigger and bigger magnets. If we go back, one of the questions I like to ask at some point in the semester, like the final exam, is what changes when you go to bigger fields, when you go to bigger magnets? And the first thing I ask is, does the Larmor frequency of the nuclei, does that change as a function of magnetic field? Yes, right? Because we have 300 megahertz magnets and 600 megahertz magnets and 900 megahertz magnets. So the Larmor frequency changes. Does the chemical shift change when I go to different magnetic fields? Yes, no? That's sad, because this was just last week. No. The chemical shift doesn't change. The whole idea of the chemical shift being the distance between peaks over the operating frequency of the instrument is that a methyl peak that shows up at 1 part per million shows up at 1 part per million regardless of the magnetic field. So chemical shift doesn't change. Okay? The third thing that doesn't change then is the coupling constant. So the coupling constant does not change as we go to bigger and bigger magnetic fields. And that's something to remember. Okay. Then, the other thing with a coupling constant, or that distance, is that if you have two hydrogens that split each other, then if they're neighbors and they're splitting each other, their multiplets, their doublets, triplets, or quartets are going to have exactly the same distance between the peaks. They're going to have the same coupling constant. So if you have in your spectrum, if you have a bunch of different triplets and you have a bunch of different quartets, then you could find out which triplet goes with which quartet. In other words, which two hydrogens are neighbors by measuring the coupling constant, because the coupling constants have to match up if the two things split each other. So if I have 3 or 4 ethyl groups, because the ethyl group is a triplet quartet, if I have a number of different ethyl groups, in theory, I can find out which CH3 goes with which CH2 by measuring the coupling constant and then matching them up. Okay, so when two hydrogens split each other, they have to split each other by the same coupling constant. They won't have the same pattern necessarily, but they will have the same distance. So that's an important thing about this idea of the coupling constant. We're not going to use the coupling constant nearly as much as we could, but it is a pretty important feature. And one of the things that there are now are tables of coupling constants for different types of hydrogens. Because I can make these tables, because it doesn't change as a function of magnetic field. And one of the important areas where you see differences in coupling constants is cis and trans. How do you determine whether a molecule is cis or trans? Well, you can do that by looking at the coupling constant between the hydrogens that are attached to the double bond. If it's cis, then they have a coupling constant of 10 hertz. If they're trans to each other, it has a coupling constant of 15 hertz. And so if you find which peaks are which, and you find the patterns, if you measure the distance, you can tell whether your molecule is cis or trans simply by looking at the coupling constant. So that's one pretty powerful application, is to try and figure out whether a molecule is cis or trans. You can also look at substitution patterns around benzene rings as to whether things are ortho or meta by looking at the coupling constant and different between 2 hertz and 8 hertz. Turns out that para coupling has a 0, but you don't know what ortho, meta, and para are yet, but you will soon enough. Okay, so the coupling constants can actually be used to figure out more details about the structure. And we'll just leave it at that. All right, last thing. Let's start with propane. Okay, can we predict, first of all, how many sets of equivalent hydrogens we have? And then, can we predict what their splitting patterns would be? Well, for propane, how many different sets of protons do I have? How many sets of non-equivalent hydrogens do I have? Just 2, right? Because I've got the methyl groups as A and the CH2 as B, because there's a mirror plane of symmetry that would make the 2 methyl groups equivalent to each other. Okay. What would be the splitting pattern? Well, how about for the methyl groups? How many neighbors does the methyl group have? 2. Right? The methyl group is attached to a CH2. So it has 2 neighbors, which means it would be split into a triplet or 3 peaks. Okay, so it's got, the CH3s have 2 neighbors, and that means that it would be a triplet. Now, the CH2 is a little trickier because what we have to realize with the CH2 here, with the B hydrogens, is that it has 2 neighbors of CH3 groups, but those CH3 groups are equivalent to each other. And this is a case not like the isopropyl CH. In this case, both of these methyl groups are equivalent to each other, so it, in essence, has 3 neighbors. Okay, because it just sees one CH3 group because the 2 CH3 groups are equivalent. That's the general rule. The exception is the isopropyl group. Okay? So that means with having 3 neighbors, the CH2 would be a quartet. It would have 4 peaks. All right, so that's pretty straightforward if you just remember that if a hydrogen has 2 equivalent groups on either side of it, you just treat it as if it was one of those groups. But now let's make this a little bit more complicated. Now let's make this 1-chloro-propane. So now let me take away the symmetry so that I would have now 3 sets of hydrogens. Okay, if I have 3 sets of hydrogens, what are the splitting patterns of those going to be? Well, let's take the ones on the end. What would the splitting pattern for A be? For the CH3. It has what as a neighbor? CH2, so it has 2 neighbors, so it would be a triplet. Okay, so it's going to be a triplet. The CH2 attached to the chlorine. What's it attached to? It's attached to a CH2, which means it has 2 neighbors, which means it's going to have 3 peaks. It's going to be a triplet. about the one in the middle, the CH2? Well, the CH2 in the middle, B, is actually not going to be a singlet, doublet, triplet, or quartet, because it has two non-equivalent groups attached to it. It's got a CH3 group on one side, and it's got a CH2 group on the other. Now we can estimate the number of peaks that should show up for that by adding up the total number of neighbors. And so if I add up the total number of neighbors for the CH2, I've got 3 on one side, 2 on the other, which means that for the estimate, I have a grand total of 5 neighbors, and that means that I would have 1, 2, 3, 4, 5, 6 peaks. Okay, I'm going to have a 6 peak pattern. And I'm going to put an approximately 6 peak pattern because when we get into hydrogens that have non-equivalent groups on either side, that's an estimate. It could have its 6 peaks, and I usually put a plus or minus 2 on that. So that means that the peaks could be anywhere from 4 peaks to 8 peaks. Okay, that's the estimate. Now, why is that? Well, the reason that is because we have what's called complex splitting. Or in the previous slide, we have to use what's called the splitting tree. Let me give you an example of this. So, I'm going to go to another clean slide here. How about I have a CH that's in between 2 non-equivalent CHs? Okay. So if I have a CH that's split by 1 CH on one side and 1 CH on the other side, what's going to happen is this. This CH is going to start out as a single peak. But then the CH to the left of it is going to split that peak into a doublet. Okay, there's one neighbor to the left, and so this peak gets split into a doublet. That's the n+1 rule. But now, it's also being split into a doublet by the peak on the right. So the first peak, and I'll call this A and C. So in the middle's B. So B starts out as a singlet, but then it's split by A into a doublet. But then it's further split by C into another doublet. So that means that each one of these peaks from the first doublet, they now get split into doublets. So the pattern for B is what we call a doublet of doublets. In other words, it's split into a doublet on one side, and it's split into a doublet on the other side. So the first doublet gets split into more doublets. Okay, so we end up with a doublet of doublets. You can kind of see that here in this pattern. I'd end up with 2 peaks and another 2 peaks. So it would be a doublet of doublets. And many, many, many years ago, when I first started teaching Dr. Weaver, who's long since retired, he used to call these things like a 2x2. The students would say, well, what are these 2x2 things? And I looked at them and I go, I don't know. I said, where's he using this term? Oh, in splitting patterns. Oh, okay, that means a doublet by doublet. Or a doublet of triplets, or a quartet of triplets, or a quartet of quartets. Okay? Simplest case is a doublet of doublets. So that CH gets split, a doublet this side, doublet that side. So it ends up as possibly 4 peaks. Now, the final positions of those 4 peaks depends upon the distance between the first doublet and the distance of each of the 2 other doublets. and that is the coupling constant. So since the coupling constants are different, those peaks, those 4 peaks, can end up in different places. For instance, here's the first doublet, here's the second doublet. Okay? And they have to be the same distance. But the distance between the doublets can change as a function of the coupling constant. So if my doublets are far apart, I end up with 4 peaks as a doublet of doublets. But as those peaks move closer and closer together, the 2 middle ones could overlap so that I would end up with what looks like a 1 to 2 to 1 triplet. So sometimes you see a doublet of doublets, sometimes you see what looks like a triplet, although it's really a doublet of doublets. And so depending on those distances, you can end up with peaks that look like that. The point here is that depending upon the coupling constant, you can end up with anywhere from 4 to 3 peaks in this system. Now it gets more and more complicated because what I have in the case before this was I have now for this CH2, this is really a quartet of triplets. Or a triplet of quartets, it doesn't matter. So that means that when I split my first peak into either a triplet or a quartet, and I'll split it into a triplet, that means that each one of these other peaks now gets split into a quartet. And so what we have is a bunch of overlapping peaks. But they usually overlap such that you see anywhere from 6 to 8 numbers of peaks. Okay, the only example I can give you is if, let's say I've got, because I don't have 3 hands, so I can't do like a triplet of quartets, but I can do a doublet of quartets. So with the doublet of quartets, here they are. If they're far apart in one of the coupling constants, then I'll see 2 distinct quartets. But as they move closer and closer together, I could end up with 1, 2, 3, 4, 5, 6, 7 peaks. Or if they start to overlap this way, I could end up with 1, 2, 3, 4, 5, 6 peaks. Or they could overlap and I could end up with 1, 2, 3, 4, 5 peaks. So depending upon the coupling constants, if they overlap a lot, I'll end up with a lower amount of peaks. If they overlap nothing, then I'll end up with 2 sets of quartets. So that's why I'm putting a plus or minus value on it, is because depending on the overlap, you could see 6 peaks, you could see 4, you could see as many as 8. So this is complex splitting. For our purposes, we can estimate by simply totaling up the number of neighbors. But the one thing about these complex splitting patterns is they tend to be clean. In other words, you'll see symmetry around the peaks. If you see peaks that don't look symmetric, it's because you have 2 distinctly different hydrogens that are now overlapping. So as we go through spectra next week, we'll see some where there's a nice clean pattern, we'll see others where there's not. Okay? But that's what happens if you're a hydrogen in between 2 non-equivalent groups. You suffer from complex splitting. And so the complex splitting, we're just going to estimate, but I need to show you the trees, at least the basic ones, to understand why we can only estimate. Okay? And at least you don't have to like get graph paper out and draw a triplet with a 3 hertz difference between the 2 and then draw the quartet with those so many other hertz and try and overlap the peaks and see how they work. Okay? We're not going to go that far. And so here's an example. Here's doublet of doublets that occur in the molecule styrene. Notice that when the coupling constant is, let's say, 17 hertz and 11 hertz, what you see is you see 4 peaks, and you can kind of pick out the doublet of doublets from that. When the other second coupling constant is like really small, the pattern on the left looks like a doublet of doublets. You can clearly see that. But on the one on the right, it's still doublet of doublets. It's just getting harder to see what's what. Okay, so it occurs because there's two sets of coupling constants that are basically spreading the peak out. And if you have to get more and more into detail about this if you want to truly understand it, which we're not going to. We're just going to estimate. Okay. All right, so that's the first part of coupling. What we will do next week is I'll give you some spectra of pentyl and butyl bromides. And so if you think about for butyl bromides, there's 1 bromobutane, 2 bromobutane, there's isobutyl bromide. There's all the different alkyl groups. What we're going to do is look at the patterns and try and figure out which pattern goes with which type of NMR spectrum. So we use the coupling, we use the integration, we use the whole 9 yards. So there won't be a homework assignment for this coming week, but then after next week we talk about it, there'll be a homework assignment for the following week. Okay. And I'll post, this online sometime within the next couple days, so when that time comes you can go back and listen again.